Picture a 19th century ship cutting through the open ocean. Look up and you see a sprawling cloud of white canvas catching the breeze. But look down and you see something contradictory, a thick column of black smoke belching from an iron funnel right in the middle of the deck. For thousands of years, humanity crossed the oceans using wind and muscle. The ships grew larger and rigging more complex, but the power source remained at the weather's mercy. The invention of the steam engine offered a mechanical heartbeat that a vessel could carry on board, independent of the tide or the breeze. The earliest steamships were paddle steamers. They used large rotating wheels fitted with flat wooden blades to push the hull forward. On calm, flat inland rivers, they worked perfectly. Both wheels sat evenly in the water and maintained a consistent grip. But put a paddle steamer on the open ocean, and the design falls apart. When a ship rolls in heavy sea swells, one paddle wheel lifts entirely out of the water, spinning uselessly in the air. The opposite wheel plunges far too deep, fighting against the water pressure. The engine loses enormous amounts of power trying to drive a ship that is violently rocking side to side. The ocean introduced a second mechanical flaw. Steamships had to burn enormous stores of heavy coal to keep moving. Over the course of a long voyage, a ship would burn through hundreds of tons of fuel, constantly growing lighter and rising higher in the water. With every passing day, the paddle wheels lost their grip as the ship lifted closer to the surface. Early steam engines were too inefficient, and paddle wheels too sensitive to conquer deep water alone. To travel across the globe reliably, engineers built a transitional machine, a hybrid that married the free power of ancient wind with the mechanical force of industrial fire. To make steam work on the high seas, designers realized they had to get away from the unpredictable surface of the water entirely. The propulsion mechanism had to move beneath the waves. The solution was the screw propeller. Submerged at the extreme rear of the hull, it uses angled rotating blades to convert the engine's spinning force into forward thrust. Because it sits completely underwater, it maintains a firm grip whether the ship is rolling in heavy swells or riding high with empty coal bunkers. The British Royal Navy staged a massive physical demonstration in 1845 to end the debate over which method worked best. They lashed two identical ships stern to stern, one with paddle wheels, one with a screw propeller, both throttled up to full power. The propeller-driven ship easily dragged the churning paddle steamer backward at over 2 knots. Even with a vastly superior way to push through the water, a massive economic bottleneck remained. Those early engines burned coal at an astonishing rate. If a captain tried to cross the Pacific Ocean on steam alone, the ship would exhaust its entire fuel supply in a matter of days. To manage fuel costs, hybrid ships relied on a clever mechanical workaround known as up-funnel, down-screw. When the wind was strong, crews would collapse the ship's exhaust funnel down to the deck to reduce wind resistance, hoist the heavy iron propeller entirely out of the water so it wouldn't create drag, and unfurl the sails. The HMS Warrior, launched in 1860, is the ultimate example of this design. She was a massive ironclad warship. Under steam, she was the deadliest vessel afloat, but with her propeller hoisted and her sails set, she traveled as cleanly as any clipper. For decades, relying on both sails and steam engines was the only economically viable way to cross the oceans. But far below the clean, breezy wooden decks of those hybrid ships, a completely different world was taking shape deep inside the iron hull. Tending the ship's furnaces required a specialized maritime worker known as the Black Gang. In an enclosed environment where temperatures routinely exceeded 50 degrees Celsius, these men crawled through the bunkers, constantly shoveling mountains of coal to feed the fire and keep the ship balanced. Workers spent 4-hour shifts surrounded by the deafening hiss of escaping steam and the heavy thud of the machinery. They shoveled continuously, lifting tons of fuel by hand just to keep those inefficient engines turning over. To free ships from the wind and to get more distance out of the Black Gang's grueling labor, engineers had to extract more mechanical energy from every single piece of coal. The breakthrough came with the invention of the compound and later the triple expansion steam engine. This schematic outlines the physics of a triple expansion engine. Instead of venting high-pressure steam after pushing a single piston, The engine routes that steam through 3 sequentially larger cylinders. As the steam expands and cools, it pushes a larger piston each time, squeezing nearly every usable calorie of energy out of the vapor before exhausting it. These complex machines drastically improved a ship's power-to-fuel ratio. With a triple expansion engine, a vessel could finally generate enough sustained force to drive large steel ships across open oceans on a fraction of the coal. By drastically reducing the rate of fuel consumption, engineers made long-distance steam travel economically practical without the need for wind. Efficient steam power physically reshaped global commerce. The turning point occurred in 1869 with the opening of the Suez Canal in Egypt. This map illustrates exactly why the canal killed the sailing ship. It provided a massive, direct shortcut between Europe and Asia. But the waterway is incredibly narrow, confined, and often windless. Sailing ships, which needed wide arcs to catch the trade winds around Africa, found it impossible to navigate. Steamships powered straight through. As the steamship fleet grew, coaling stations were built in major ports around the world. With reliable places to refuel positioned along every major trade route, the engine's final logistical weakness vanished. The economic viability of the pure sailing ship collapsed. Maintaining complex rigging required a massive, highly trained, and expensive crew. Steam cargo liners, relying on steady operations and cheaper steel hulls, easily priced the tall ships out of the market. The unpredictable nature of ships racing across the ocean to catch favorable weather gave way to scheduled shipping lines. A merchant could load cargo onto a vessel and know precisely what day it would arrive on another continent. The turn of the century marked the end of the ocean's reliance on the variable power of the wind. In its place, the steam engine offered a level of predictability that allowed global shipping to run on a set schedule. Steam had won the ocean. But the massive coal-fired systems driving these modern fleets were still heavy, filthy, and required a massive amount of manual labor to maintain. To push the shipping industry forward, engineers required a denser, cleaner fuel. They needed a liquid that could be pumped through automated pipes instead of hand-shoveled in a sweltering boiler room. In 1892, a German engineer named Rudolf Diesel patented an internal combustion engine that solved the problem. His machine compressed air with such intense pressure that it ignited liquid fuel automatically, without a spark. The era of the coal shovel was ending. In our next episode, we will trace how the shift from furnaces to fuel pipes allowed ships to become larger, faster, and more automated, creating the high-volume transport network that moves 90% of global trade today.